Hi, welcome back everybody. We're on episode 12, class 12 of Uncertainty and Probability Theory, the Logic of Science. This week we're going to do some psychic card guessing experiments, and we're going to finally return to assigning numbers to probabilities. You remember the only numbers we can assign so far is 0 for local falsity and 1 for local truth. Last week, I emphasized, and I want to slow this down. I have to slow it down because I cannot emphasize this enough, that all probability takes this schema. We all start with some proposition that we want to know something about, something in which we take an interest. And we accumulate or have or assume evidence. We always assume it is true, some Q, which relates to the uncertainty of this proposition of interest. I wish I wouldn't have picked P and Q so many years ago. I can't even remember why. I did. And there's no right or wrong answer per se, except when we fix the P and Q. If I give you a fixed, hard, rigorous definition of a P and a fixed, hard, rigorous definition of a Q, then the probability is utterly fixed. So last week we went over the homework about the one son born on a Tuesday, the probability of both the children being boys, that kind of thing. And there was some confusion and consternation and some flummoxedness and this kind of thing. But there was also a lot of anger. I got some angry comments at various places, most notably Twitter. People become angry over this, and that just boggles my mind. What are you doing with these strange formulas trying to overturn everything we know? Look, you know, I don't charge for these things. People don't have to watch. I understand there may be disagreements, but if you're going to become angry over this just encapsulated for me the perfect sort of science in miniature. This is how science works. People latch onto a position, and if the answer doesn't accord with their intuition, and remember, intuition is one of the highest forms of thought that we have, but can be an error, which it is in this case for some people. If it doesn't accord, the answer doesn't accord with their intuition, they become quite angry. And they refuse to listen to absolutely anything to do with which overturn their intuition. And so I understand that because, again, when we're talking about intuitions and induction and the like, we're talking about our deepest thoughts. And so things that outrage them are naturally going to attack us more viscerally or affect us more viscerally. But that's just the way it is. That's why I was so careful. And we're only on episode 12 here, and we've just taken our time, bit by bit by bit. We've done very little. We've only got 2 numbers for probability. You know, 0 for local falsity, 1 for local truth. That's it. And we haven't done anything. I've been very careful talking about building this up step by step by step, showing you everything, the possible way that thought can go right and wrong on this kind of thing. So we're going to do the same thing today. Now, the example I gave you for homework, and only one person got it, and he goes by I could call out his name because he used it in comments, Nate. My heart soared like a hawk. It's always a delight for anybody who's teaching this kind of stuff to find somebody who gets it, and Nate did. The idea was there's a deck of 52 cards, ordinary playing cards, and a psychic is going to guess each of these cards. I'm going to pick up a card, and the listener, are going to pick up a card, see what it is, and you're going to think the thought of the card, and I'm going to, as the psychic, guess the card. Okay, so she guesses 10 guesses, and got, I think it was 4 right and 6 wrong. And every time she got one right, she got a chocolate. And when she got one wrong, nothing. And I asked, the proposition of interest was guessing card. We did 10, so this would be card 40. We did 10 to be 42 left in the deck, right? So guessing card 42 right, or something like this. Okay. Or is it 41? Doesn't matter. Now, and we want to know the probability of P given Q. Now, as it stands, I told you I'm interested in your thoughts on this, because your thoughts, your way of arguing about this are what's important. You don't have the math. I'm going to provide a link to the math at the end of this description for this, and it's quite complex. We haven't reached it. We'll get to that level eventually. And in order to solve this question, it depends on what you mean by some of these things in here. There's no right or wrong answer because the Q can vary. And now I gave you the hint, how to solve these questions. Don't try to jump to the right answer in these things. A lot of people were saying that this was equaling to 1 over 42. That's the right answer to a different question. That says I only have 42 cards in the deck and I'm going to guess one. What's the chance I get one right? Well, that's 1 out of 42. That's true. But that's not the optimal strategy when I have had feedback. And so I said, don't try to solve these hard problems just jumping out and try to figure them out. Try to solve a simpler problem that you could turn into the complex problem by either going to the limit or just adding conditions and cases and things like this, and you'll find you'll gain a lot more insight. And that's how mathematicians, that's how we solve theorems and the like. We don't necessarily try to jump to the most complicated case. You do the simpler ones and you build up, you build up. So instead of a deck of 52 cards, here I'm going to show you a deck of 2 cards. And this is not in any way a trick, nothing like this. I'm going to shuffle these here. I'll shuffle them behind my back and I'll shuffle them. Now I got 2 cards and I'm going to hold this up and you're going to look at it. Okay, you're going to look at that. And you psychically, from the future, using pilot quantum waves, I should say, are going to send this back to me and I'm going to guess. Now, before I do that, what's the probability I get it right? Well, if I have psychic powers, the probability I get it right is 100%. So that's one Q. All right, but supposing I don't have psychic powers and I'm just guessing. See, different Qs, different Qs. Well, the probability is 1/2. Okay, so let me guess here. I'm going to say the king. There's a king and a queen of can't quite get it. The pilot waves are being interrupted by this damnable cold front that's come in. So I'll say the king. Ah, I'm wrong. And you told me I'm wrong. I don't get any chocolates. Now, what's the probability I get this one? There is none, unless I say I remember what just happened. If I remember what just happened with that feedback, I know that I was wrong about that. I know I said the king. I know there's only a king and a queen. And if I'm paying attention, the probability I get this one right is 100%. It's no longer 1/2. It could be 1/2 if I'm some NPR listener or something like this, not paying attention, and I don't know how to use the feedback, and I'm a naive poker player or something like this. I may forgot what I said on this one and say, oh, well, it's now I guessed the king the first time, I'm going to guess queen the second time. The probability is only 1/2 or stupidity. So it depends on the cue we pick. And the real question is, it's exactly the same. Let me add a jack in here. You shuffle them all. Whoops. Shuffle them all up, and so I really will do this here. All right, I'm going to send you that. You guys are going to use that pilot wave business to send it back again. This time I'm going to guess jack. It's the king. I'm wrong. Now, what's the chance I get the next one right? Well, the king's eliminated. The king is eliminated. I saw that it was the king, and so now I'm going to leave you this. I'm not going to solve this for you. I'm going to leave you the homework of guessing what's the probability I get this next one right. It depends. I could have just been told I was wrong on this, and that gives me one cue. Or I could have been shown, aha, it's the king. And that gives us a different cue. So there's different optimal strategies depending on the feedback we get. It's very complicated, isn't it? And there's actual math that you could use, just raw information like this. There's only a number of cards you know. There's right or wrong feedback, and then there's actual card feedback. And the guy who solved this, or the guys I should say who solved this formally, Percy Diaconis, Ron Graham. Percy Diaconis was briefly an advisor of mine when I was at Cornell. Shared an interest in amateur magic. The real probability, of course, if you entertain is if you're dealing with somebody like me. I have an acre of books. I don't have an acre of books. I have a big shelf of books just on card tricks alone. Never trust anything. There's nothing. absolutely never trust anybody with cards for any reason. There's so many ways to cheat. I don't even know. I mean, there's literally tens of thousands of ways to cheat with cards, and ways that you'll never perceive unless you start studying the question over years. So that's it. That's this homework. It's not simple. Nate got it. He started by doing exactly as I said. He started with this simple problem. I think he started with 3 cards, perhaps, or only 2, and then worked his way up to something towards the right answer. Although I promise you, none of us had the math. I wasn't interested in the math. I was interested in your reasoning. That's how you have to attack all these things. Okay. Wow. We did all that. This is why I have to slow down. I'm not even to the main part about the proportional syllogism here today. I don't even know if I'm going to get to it. So here is my new evidence. I have a Metalunan interoctor, oscillator, which must take either state 1 or be in state 2 or be in state 3 or be in state n. It must be in one of these states and it must take one of these states. That's the information we're assuming is true. We're not allowed to substitute other information. Well, what if the machine breaks or something like this? No, that's not part of the information we're assuming is true. That's an entirely different Q. We'll get an entirely different probability. We're using this Q. And my proposition of interest is the state equals SI. And for short, I'll just write SI. I hope you can remember that. So I really want something like the probability that SI, that is, see, we're getting more and more into math, but we must never forget the math stands in for these propositions. We're doing propositional calculus here. But it's easy to forget because the math can take on a life of its own. The deadly sin of reification is always with us. And this Q. Well, we don't know. However, we can argue, whoops, I'll just put this as a, if you can read my notation here. This is called the proportional syllogism. The probability that it's in state I is going to be the same as in state J, given this information that we have. Now Hempel, Carl Hempel, I think called it proportional syllogism, or the symmetry, or we proved this through the symmetry of individual constants. Anyway, he first noticed this this phenomenon, tried to give it a, thinking about the epistemology behind it all. This is something. Now we can prove this. There's this is the important point about us. We're not going to do it today. We don't have time. We're already halfway through this lecture. I haven't even got half of this done. So we can prove this by something called, through those symmetry of individual constants, and David Stove has done that in his book, The Rationality of Induction. In the second half of this book, which is of course badly titled for us because the second half of the book is all about probability, and you wouldn't know that unless you cracked it open. We can prove this. And I'll go to some way to giving you a hint of it today, possibly next time, because we're already running out of time. But if you can't see this, not everybody can. Not everybody can. Some people quail at this kind of a thing. Not everybody can see every axiom. All right. Not everybody has the same intuitive jump. All right. When we meet an induction, when we meet a universal, we're always moving from these limited, finite examples that we have, and we're jumping to infinity. It's a big deal. We've gone over it bits and parts, but and I didn't emphasize it as much as I think I wanted to in this class because we're trying to get to the math about the probability and so forth. But I'm going to spend a special, I'll write a separate article on all this kind of a thing and our ideas and reenchantment and so forth, because it's really quite profound about how intuition and induction overrule or are far above rationality in simple matters like logic and so forth. So I'm not claiming everybody can see this. David Stove had a proof of it with a slight twist, and I'm not going to be able to get to that today, or maybe not even next time. James tried a proof of it, and I think he failed. Percy Diaconus tried a proof of it, and I think he failed. I have the details in my book about how they exactly failed, and we'll get to these kind of things. Because they slipped in an assumption, which is basically this, and their arguments became circular. And we'll get to those in time. So for right now, though, let me see what I can do about this. So the proportional syllogism, you're going to have to memorize this, my friends, because I don't have a lot of room here on this board. You can always pause and go back and so forth. It gives us, this is, again, we're going to use the same kind of proportional syllogism argument to get probabilities. So here's another cue. It's that all Martians wear hats. And George is a Martian. And I want the proposition interest to be, I'll do it this way. Okay, so George wears a hat. So with this Q, the probability of P given this Q is of course 1. We just have a standard syllogism. But let me change this. Instead of all Martians wearing hats, I'm going to say 90% of Martians wear hats, and George is a Martian. George wears a hat. And this changes to 90.9, 90%. It doesn't matter whether you're talking about percents, really. I mean, it does, but for our shorthand purposes here, 0.9 is 90% are close enough. This is another, we derive this or deduce this from the proportional syllogism. So here we are grabbing math. And the reason we can think about this is we have this symmetry of individual constants. I'm not providing the proof yet. I'll get to the proof next time or the time after. I'm just showing you where the proof is going. So I can change this Q. I can give us a Q prime, if you like, where it's exactly the same, but Sally is a Martian. And we would at least agree that the probability that George wears a hat, if you like, and this Q equals the probability that Sally wears a hat. If I give the same Q but substitute in Sally, these probabilities should be equal. There's nothing to distinguish these constants from one another in the language implicitly or tacitly or anything like that. And so they should share the same probability. And that kind of thing leads us through, formally, to a proof that this will be 90%. So I told you for the past few weeks that we were going to assign numbers to probability. And it was going to be what most people's intuition would be like. And there was going to be no real surprises, and there can't be any real surprise about this, I don't think. It's exactly what we thought. So now let's move to that and assign even more probability, more numbers to these kinds of things. All right. I don't think there's any problem. I mean, you either see this stuff or you don't, and you might quail at some of this stuff, but I promise you I will give you the proof to deduce these things, and I'll show you where the other guys have went wrong on this. So in logic, if I have an argument from Q to P that's valid and sound, if I add a necessary truth, where T is some necessary truth, and we did the difference between necessary and local or conditional truths a long time ago. Go back and review those lessons. I add nothing. The argument is still logic, still sound and valid. Adding a necessary truth to an argument doesn't change it. It's like multiplying an algebraic equation by 1. This is just sort of standard logic 101 thing. So I can have the old saw, you know, all men are mortal, and Socrates is a man, and therefore Socrates is mortal. Here's our old favorite syllogism. And I could add to this something like A is A for some proposition A, as long as A is not self-refuting or something like this. You know, a constant. This is a necessary truth that the proposition A is A. Or I could say another one is whoops. This is sidewalk chalk I got, which is very nice. A or not A is true. And this is true for any A, because either A or its opposite, its logical contrary, I should say, is true. This doesn't change the syllogism whatsoever. And since probability is logic, adding a necessary truth to a logical or a probabilistic argument won't change it. So, for instance, I could have lots of other things. I mean, there's lots and lots of things. You know, for instance, I think I used in the book, either Mars is 12 parsecs away from Earth or it isn't. That's true. It's always true. Either unicorns like chocolate or they don't. That's true even if there are no unicorns. It's a necessary truth. Or I could have something like this, a proposition A or not A. Any kind of proposition in there as long as it's not self-refuting. So in our probabilistic calculus, same as the logical calculus, if I have some argument where I'm trying to calculate this, that's going to be the equivalent of if I have this, I just add some necessary truth to it. Whatever we have deduced for this, whatever it is, it's going to be the same if I add to our list of evidence a necessary truth. And one particular necessary truth, which is a very popular one, is Q. We could do this, P or not P. Well, that's an interesting one. Suddenly, people's mind becomes boggled when we put it. We've only stuck a necessary truth in here, but suddenly minds boggle. What is not the case is this does not equal the probability that P and P or not P. And in particular, this does not equal 1/2. We have said that either P or not P is true. This does not make the probability of P 1/2. From misunderstanding this comes lots of logical paradoxes and the like, and we'll get to some of these paradoxes when we talk about what probability is not. But it's just not the case. This is a truth. We can't deduce anything. The only thing we might be able to deduce is if P is something itself contingent. Something about the universe that's observational, say, or something like this. We may be able to imply that from P or you know, not P, we imply that that's actually equivalent to P or not P and P contingent, from which we might get P given P or not P and contingent is in the interval 0, 1. We may be able to say that if this is contingent, we may be able to tacitly deduce a premise in here, an additional premise that this implies, and therefore this is going to be contingent, therefore it's not necessarily false, which would get a 0, or not necessarily truth, which would get a 1, but it could be somewhere in 0 to 1. But we just don't know the number because all we have is that it's P or not P. And this tells us nothing. It's a necessary truth. So let's make sure we understand exactly what that means. I have to erase all this again, and we're just about to end here. I'm not going to be able to get to the best part, though. Well, I'll leave it as homework, and then this will make a nice segue for me. So, so here is another necessary truth. I'll give it just a thing here. Our Metalunan interoctor might be in state Sj. That's a necessary truth because the might implies or might, this is the implicit or might not be in Sj. This is just from the language that tacit premise comes to us, or the implicit premise in this, implicit in the might, meaning it might not be. So this is, if we are in particular trying to calculate the probability it's an Sj, given this t, does not equal 1/2. Because I might then change this, I can add this, it might, S might be in Si or Sj. And it can't be that the probability that Si or Sj, or rather, it doesn't make any difference. I'll just I use Sj. Okay, let me stick with the, try not to confuse you too much. Sj and T double prime can't equal a half 2. Because then it doesn't make any sense. We're starting to, because this is just another necessary truth. Might be in S1 or Sj implies, or it might not be in S1 or Si or Sj. And therefore, we can't do this. It's not a half. All we could say is that these two equal one another, but they're not a half. All right. Now, I want you to understand that this is very crucial, and I'm running out of board space here. I want to have one more here. I'm going to put in our original Q. I have others. It's the same thing if I did T3S might be in S1 through Sn, which implies it might not be in S1 or Sn. You get that? It's either it might be in S1 through Sn, any one of those states, or it might not be in any one of those states. It's a necessary truth even if these Metalunan interoctors don't exist. And those are entirely different than S must be. S must be in one of the states S1 to Sn. This is not logically equivalent to any of these other necessary truths. This is not a necessary truth. It is a local truth that we condition on, that we accept. Must be and might be are entirely different. This is why we got to be careful about words like likely and could and all these kind of things, because they imply entirely different probabilities. We have here, and the answer is going to be, I mean, obviously the answer is going to be probability that Sj is true, given the Q that we have, is going to be 1 over n from the symmetry of individual constants and using the proportional syllogism. We're gonna prove all that. It's very obviously true, if you accept those proofs, that this is going to be the case, and it doesn't really, I don't think, interferes with our intuition too much. But for some people it might. They might say, "Wow, it could be anything." It can't be anything. It can't be anything, and we're going to prove it can't be anything. And so I haven't given you that proof. So if you're gonna carp about that, well, we haven't done that yet. But it's entirely different. This information is entirely different than this information. And we change the information, we change the probability every time. Nothing has a probability. We did that lesson. I emphasized it over and over again. I'm going to continue emphasizing it because all models, all theories, all scientific theories in particular are in exactly that shape. They're all the probability of P given Q. All of them. And if we change anything about the Q, anything whatsoever, and it's probative of P, we change the probability. That's just the case, okay? And failure to understand all these things leads to all kinds of paradoxes, which we'll come to, and other things that are just misunderstandings, and then people go off and they make wrong decisions, especially as we'll see in statistics. Okay, so here, and I acknowledge I haven't given the proof, but we'll accept the proof, just like we accept the Riemann hypothesis is true in math, and we go on and prove other theorems. We accept it as true, becomes a local truth, and then we prove other theorems based on that. They become local truths until someday maybe the Riemann hypothesis is proved true to be a necessary truth, and then all those other local truths turn into necessary truths. Remember, we did all that kind of thing? If you're not remembering this stuff, please go back. I've given you the entire book so far, my book, and up to where we are. I haven't left anything out except the references because everything's in LaTeX and it's a pain in the ass to bring the references over. But otherwise you have everything, and you have the first few chapters of James too. So I have Q. I'm going to, and naturally I brought it with me and I can't find the dumb things. I want to show you what a Metalunan interoctor is. Aha! Here, I didn't tell you what a Metalunan interoctor is, but it turns out to be one of these things. Can you see it? This is a Metalunan interoctor, which must take state 1, which equals a 1, state 2, which equals 2, and state 6, which equals a 6. And I want to know the probability that it takes state 6, given this Q and this word, fair. People love to add this. I'm going to roll a fair die. I want you to give me this probability. And we're going to accept all those proofs that are to come as true. You do that, and we'll meet not next week, which is going to be the weekend right after Thanksgiving, 4th of July. Nobody will be around anyway, so I'm not going to put up a lecture. Maybe I'll put up something else just for fun, like a doomsday argument. But so it'll be 2 weeks from now, and I will reveal the answer to this. That's it for now. There's more information down there. And if you have questions, again, I'll answer them on the next week's lecture. We're going slow. We have to go slow. This is going to take a while to get there, okay? Because I don't see your faces and I don't know what else to do. So we have to take this bit by bit, but we'll get there. You have to review, though. You have to think about this stuff. It's not so easy. There's not much math, so it fools you into thinking you don't have to think so much, but you do. All right, that's it for now. See you in 2 weeks.